So the problem is g of s is given as g of s equal to k into e raised to minus 0.2s divided by s into s plus 2 into s plus 8. Find gain k of the system. Find gain k of the system for which the system is stable and gain margin is equal to 6 dB and phase margin equal to 45 degree. So we have to find out the gain of the system k for which the system should be stable and gain margin is equal to 6 dB and phase margin is equal to 45 degree. So in this question you can observe that there is an exponential term in the numerator. So when an exponential term comes in the numerator, it changes the angle of the system. It will contribute an additional term for finding out the angle of the system. So the first step is first we can rewrite sinusoidal transfer function g of j omega. Let us assume that for the time being, let us assume that k is equal to 1. Now we can write g of s is equal to, write it into 1 plus st format. So e raised to minus 0.2s divided by 2 into 8 into s into 2 into 8 into s, this time is s actually, 2 into 8 into s into 1 plus 0.5 s into 1 plus 0.125 s. So when we rewrite the equation will be 1 by 2 into 8, that will be equal to 1 by 16. So g of s will be equal to 1 by 16, we can write it as 0.0625 into e raised to minus 0.2 s divided by s into 1 plus 0.5 s into 1 plus 0.125 s. So when you write it in g of j omega or sinusoidal transfer function, the equation will be g of j omega equal to 0.0625 into e raised to minus 0.2 j omega divided by j omega into 1 plus 0.5 j omega into 1 plus 0.125 j omega 1 plus 0.125 j omega. This is the expression for g of j omega. Now we have to write the magnitude expression. So before that, before writing the magnitude expression, we know e raised to j theta, or when you write in modulus amplitude form, r e raised to j theta. This is the modulus amplitude form. The magnitude of this part is equal to r. This is the magnitude of the above term, and the angle of the above term is theta when you are writing in modulus amplitude form. So in similar case we can write e raised to minus 0.2 j omega. So the next step we have to write the magnitude and angle of g of j omega. So magnitude of g of j omega equal to, so in the magnitude, when you write the magnitude part, when an exponential term comes, you have to add the constant of that exponential term to the whole system. Then it will not affect much in the magnitude part. So when we write the magnitude expression, it will be the gain of the system. When k is equal to 1, what is the constant term that comes in the numerator? That is 0.0625, then divided by omega into square root of 1 plus 0.5 omega square into 1 plus 0.125 omega square. This will be the magnitude of g of j omega, magnitude part of g of j omega, and angle of g of j omega. So this before writing the angle of g of j omega, what is the angle of e raised to minus 0.2 j omega? The magnitude of this part, the magnitude e raised to minus 0.2 j omega, the magnitude part of this is equal to actually 1, because here the coefficient of this term is 1. So magnitude is 1 and angle is minus, angle of this term is minus 0.2 omega in radians. The angle of this term is minus 0.2 omega in radians. So we have to convert it into degree. So we can convert it into degree by multiplying by 180 by pi. So the angle of this term will be minus 0.2 omega into 180 into 180 by pi degrees. So this is the angle of the given expression. Now we can write the expression for angle of g of j omega. Angle of g of j omega, that is equal to minus the angle of the term, that is minus 0.2 omega into 180 by pi. That is the first term, that is the angle corresponding to the exponential term, that is in degrees. Now there is a first order term, that is an integral factor in the denominator, or an s factor in the denominator. So corresponding to that s factor, there will be an angle 90 degree. Now corresponding to the first order term, that is 1 plus 0.5 omega, the angle is minus tan inverse 0.5 omega and minus tan inverse 0.125 omega. This is the expression for angle of g of j omega. The next step is we have to find out the table corresponding to different values of omega. So before that, we have to find out the corner frequencies omega c1. So 1 by 0.5 is 2 radian per second. The first corner frequency is 2 radian per second, and the next corner frequency, that is 1 by 0.125, that is equal to 8 radian per second. So I am selecting omega L, that is the lowest corner frequency, as 0.1 radian per second. So the next step is to draw the table that is corresponding to different values of omega. So for different values of omega, we have to we have to find out the magnitude in g of j omega and magnitude in decibels and angle. So here you can see that when omega is 5 radian per second, you can see that the angle is minus 247, and when omega is minus when omega is 8 radian per second, the angle is minus 302 degree. So here you can say that the angle keeps on increasing. This is because of we have an exponential term in the numerator, that is e raised to minus 0.2 omega j omega. So corresponding to that term, the angle goes on increasing. That means for different values of omega at higher frequencies also, there will be an angle contributed by the exponential term. Hence the angle keeps on increasing, unlike the previous problem. In the previous problems we can see that the angle will be at some point, the angle will be constant at higher frequencies, but when an exponential term comes, that means with respect to that exponential term, there will be always an angle associated with the exponential term. It will vary by different frequencies. Hence the angle will not be a constant value, it keep on increasing with respect to the frequency. So the next step is we have to plot the magnitude part and phase angle part in the semi-log sheet. When you mark the scales x-axis and y-axis in the semi-log sheet, the next step is we have to plot magnitude plot and phase plot with respect to the value k is equal to 1 in the semi-log sheet. That is the next step. Plot different values in the semi-log sheet. So with respect to point 1, when the gain value is 0.1, you can see that corresponding to 0.1 frequency, gain is minus 4 dB. So this is approximately here. And with respect to 0.5, gain is minus 18 dB. Now, with respect to 0.5, the gain is 18 dB. 0.5 means approximately it will be here. Corresponding to 0.5, gain is 18 dB, and corresponding to 1, the gain is minus 25 dB. And corresponding to 8, the gain is 33. And 4, when omega is 4, the gain is minus 44. And when omega is 5, the gain is minus 48. So this is when you draw this plot, when you draw a continuous plot, it will be the phase angle plot corresponding to different values of omega. So this is the magnitude plot when the value of k is equal to 1. So the next step is to draw the phase angle plot for different values of angles and degrees. So we can know that the phase angle will not vary with respect to the value of gain k. The phase angle plot will be constant for all values of gain k. So the next step is to plot the phase angle plot for different values of omega. So when and frequency is 0.1, or we can see that the omega is 94. So it would be approximately here. And 0.5, the phase angle is 113. Minus 113. For 1, the phase angle is 135. For 2 radian per second, phase angle is minus 172. For 4 radian per second, the phase angle is minus 25 degree. So this is the approximate phase angle plot. So this is the phase angle plot for the of the given problem. So what is the next step? We have to find out when gain margin is equal to 6 dB. What is the value of we have to find out the value of gain K for gain margin is equal to 6 dB. So what is gain margin? How can you find out the gain margin? The gain margin is, so in order to find the gain margin, first we have to find out omega PC or phase crossover frequency. So what is phase crossover frequency? That is the point where phase plot crosses minus 180 degree. So in order to find out the phase crossover frequency, draw a straight line from minus 180 degree to the phase angle plot. So this point meets here in the phase angle plot, and in this point you have to we have to find out the frequency at this point. So in order to find out the frequency, plot a vertical line downwards. So we can see that here we can see that omega, sorry, we can see that omega PC is actually 2.1 radian per second. Now what do we have to do? We have to find the gain margin. So what is gain margin? Gain margin is minus of magnitude at omega PC, magnitude of g of j omega, magnitude of g of j omega at omega PC. So what is the magnitude at omega pc? In order to find the magnitude of g of j omega at omega pc, this vertical line that you have to extend to the magnitude line. So here it meets the blue line at this point, and in this point we have to plot the magnitude. We have to find out the magnitude. So at omega pc, what is the magnitude when k is equal to 1? So here you can see that the magnitude is minus 34. So the gain margin is minus of minus 34, that is 34 dB. The gain margin now is 34 dB. So this is the gain margin when k is equal to 1. Now what we have to find out? We have to find out the gain k when gain margin is 6 dB. So what will be the, when gain margin is equal to 6 dB, what will be the magnitude at omega pc? Magnitude at omega pc, and the gain margin is 6 dB. The magnitude at omega pc should be minus of 6 dB, that is minus 6 dB. So at omega pc, the magnitude should be minus 6 dB. At omega pc, the magnitude should be minus 6 dB. That means we have to add some gain to this magnitude plot, so that at omega pc the magnitude should be minus 6. That means when we plot the line, at corresponding to omega pc, the magnitude should be minus 6. So corresponding to omega pc, we can see that the magnitude corresponding to minus 6, that means at omega pc 2.1, when magnitude is minus 6, that is approximately this point. Corresponding to this point, the magnitude is minus 6 dB. That means minus 34 to minus 6. That means we have to add minus 6 dB minus of minus 34, that is minus 6 plus 34, 28 dB. 28 dB. We have to add a 28 dB to the gain plot or magnitude plot. We have to add a 28 dB to the magnitude plot. So at each of these points, corresponding to each and every point, we have to add a plus 28 dB, so that the magnitude plot will lift upwards. The magnitude plot will lift upwards. So in each of this point, we have to add a plus 28 dB in order to get the value as the gain margin as plus 6 dB. At each of these points, we have to add a plus 28 dB, so that our magnitude plot will lift upwards. So how will you get that? Because at omega pc, first we have to find out the gain margin now when k is equal to 1. That means the gain at omega pc, that is minus 34, hence the gain margin is plus 34 dB. Now we have to make it into plus 6 dB. So how can we make it to plus 6 dB? The gain margin will be plus 6 dB, that at omega pc at 2.1 radian per second, the magnitude value is minus 6 dB, that is corresponding to this. So in order to make that to minus 6 dB, we have to add a plus 28. Minus 34 plus 28 is equal to minus 6 dB. That means we have to add, at all points we have to add a plus 28 dB. So that will be approximately here, points will be approximately here. So this is the magnitude plot when gain margin is plus 6 dB. You can see that at omega PC the gain margin is actually plus 6 corresponding to this plot. And how can you find out the gain here? So in order to find out the gain, we can say that k into the magnitude of g of j omega, that is 0.0625 divided by omega into 1 plus 0.5 omega square into 1 plus 0.125 omega square, that is equal to, what is that value? That value we have obtained as approximately plus 20. Okay, so that is approximately equal to plus 20 dB. Now we can, so this is this value is not in decibels, so we have to convert this into decibels. How can we convert it into decibels? 20 log k plus 20 log 0.0625 divided by omega into square root of 1 plus 0.5 omega square into 1 plus 0.125 omega square, that is equal to 20 dB. That is equal to plus 20 dB. So when the value of omega, what is the value of omega here? When that at the starting point, when omega is equal to 0.1. So when omega is equal to 0.1, we already have the value. Okay, when omega is equal to 0.1, we already have the value as minus 4 dB, right? Minus 4 dB. So we can rewrite the equation as 20 log k plus minus 4 dB is equal to, actually the correct value will be minus 4 plus 28. Minus 4 plus 28 will be 24, not 20. The value will be 24. Because at the initial point, when you add minus 4 plus 28, it will be plus 24 dB. So we can see that this is plus 24 dB and 20 and 20 log k is equal to 28. And the value of k will be equal to 90 log of 28 by 20, that is equal to 25. So when gain margin is equal to, and the value of gain margin is equal to 6 dB plus 6 dB, we got the value of gain k as 25. So we can write here the magnitude plot when k is equal to 25. Now the next step is we have to find out the phase angle plot. So the next step is we have to find the phase angle plot. We have to find the value of gain k when phase margin is 45 degree. So what is phase margin? Phase margin is, the equation for phase margin is actually the equation for phase margin gamma is equal to 180 degree plus 5 gc. What is 5 gc? 5 gc is the angle of g of j omega at omega gc. What is omega gc? The frequency at which the magnitude plot crosses the 0 dB line. So again we have to consider the magnitude plot here. So here we can see that the magnitude plot does not crosses the 0 dB line. At k is equal to 1, the magnitude plot does not crosses the 0 dB line. So we have to find out omega gc. What is our required phase margin is 45 degree. So we can write that our required phase margin is 45 degree, that is equal to 180 degree plus 5 gc. Then 5 gc will be minus 180 plus 45, that is equal to minus 135 degree. So minus 135 degree, that we have to check in the phase plot. What is the frequency at minus 135 degree? This is corresponding to minus 140. And minus 145 degree, when minus 135 degree will be approximately here. So this is our phase angle plot. This orange line shows our phase angle plot. So minus 135 degree is approximately here. Minus 135 degree. So at minus 135, what is the frequency at minus 135? Frequency at minus 135 is 0.9. Okay, it's not 0.9, it's approximately 0.85. Frequency corresponding to, this is the frequency corresponding to minus 135. So we can write that So we can write that at 5gc, when 5gc is equal to minus 135 degree, or when the phase angle is minus 135 degree, omega gc or omega is equal to 0.85 radian per second. That means we have to make omega gc as 0.85 radian per second in order to get a 5gc of minus 135 degree. When 5gc is minus 135 degree, our phase margin will be equal to 45 degree. So we have to make omega gc as 0.85. So how can we make omega gc as 0.85? At omega gc, the magnitude of open loop transfer function should be 0 decibels. So now we can see that corresponding to this point, that is corresponding to omega gc as 0.85, that is corresponding to this point, approximately we have corresponding to the point when omega gc is 0.85, we have magnitude as minus 20 minus 24 actually. Minus 24 degree, sorry, minus 24 dB actually. So we have to make at this point the magnitude should be 0. So how can we make at this point the magnitude should be 0? We have to add a plus 24 to each and every point here, so that the magnitude will be 0. So we have to add at each and every point, we have to add a plus 24 dB, so that the magnitude at omega gc will be 0. So the points that are marked in red line is corresponding to the magnitude So this is this line shows the magnitude k. We have to find out the magnitude corresponding to this magnitude plot when omega gc is 0.85, and at that point we can see that when omega gc is 0.85, the magnitude is 0 dB. So here also we can see that the equation is, we can write the equation same as in the previous case, 20 log k plus 20 log g of j omega, magnitude of g of j omega, that is equal to that value will be approximately 20, and we already have 20 log g of j omega at omega is equal to 0.1 as minus 4. So 20 log k is equal to 24. and k is equal to anti-log of 24 by 20, that is equal to 15. So when phase margin is 45 degree, the value of k is equal to 15, and when gain margin is 6 dB, the value of k is equal to 25. And since both gain margin and phase margin are positive, we can say that the system is stable. Thank you.